The recording has begun.
All right, thanks for having me twice. It's a big
Oh,
honor.
wait. Demir needs to introduce you.
Oh,
We don't need to, but actually, yes. So, welcome everybody. My name is Damir Frizovic, and today's speaker is again Stefan Steinerberger, and he'll be talking about optimal transport and point distributions on manifolds. So, please, Stefan.
okay, thank you. So, it's very nice to be back. And again, the point of this talk is to advertise problems. Okay, I'll tell you about some results, but it's the beginning of the story. It's not the middle of the story. It's not the end of the story. And there's a lot of problems lying around here. And one can easily spend a lifetime or 5 on it. So the question is, what's interesting, and maybe there's something you find interesting, or maybe something I say resonates with you or reminds you of something that you know, and I'd be interested in seeing more. So I prepared this slide sort of not assuming that people came to the first talk, so I'll give a sort of quick introduction to optimal transport. Maybe it's also a good reminder. The question for this talk is how do you get sequences of points that are well distributed on a manifold? And for the rest of the talk, if you think about the 2-dimensional sphere and how you distribute points well on that's sort of sufficient. Okay, so if you're on the torus, there's this notion called discrepancy, and the idea is you take all axis parallel rectangles. So here's a picture, right? You have your torus and you have some points, and you take all axis parallel rectangles and you see which one deviates the most from the number, which one has either more points or less points than you'd expect, and what's the largest deviation you have. So it's a very popular notion, and it has led to very interesting mathematics. And it's popular for essentially what I think are 2 reasons. One of them is it's sort of geometrically a nice quantity, right? It's the maximum deviation over rectangles. Maybe a 3rd reason would be also historically, right? It's the first you consider. And then since the first you consider, you sort of reconsider everything in that language. And then it's also connected to practical applications, right? So there's this beautiful inequality that tells us that the integration error, this should be f at xk. Integration error is bounded by sort of discrepancy and the Hardy-Krause variation, which I won't go into. And it's a bit tricky. And one of my motivations was also like, I want to get Hardy-Krause because if you read the fine print, there is a fine print. And points that do well in sort of numerical integration, they do well because the discrepancy is small. I don't think they do necessarily well because of this, right? It's tricky. Also, second problem, what do you do on a manifold? This is all on a torus, right? It's adapted to a torus. You take the fact that you take axis parallel rectangles is a consequence of the torus. So what do you do on a manifold? And the sphere is, of course, a nice case, right? So everybody likes the sphere. And of course, there's spherical cap discrepancy, and that's a gorgeous notion and one that has well studied. And just because it is certainly a very, maybe the natural notion, right? But there are others as well, and it's not quite so clear. And it's sort of, and what if you put a small dent in the sphere, right? And the caps don't make any sense at all, right? I mean, the moment you're sort of any other manifold, what do you do, right? You could try to take local balls, but then they depend on where you are, right? The balls are not all the same. It just gets very, very tricky. And what I'm trying to propose here is, again, this time focus on manifolds, to propose Wasserstein distance as a measure of regularity. It's also geometrically meaningful, and I'll explain in a bit why. And it also connects to a numerical integration. And this time I wrote it correctly. And there's also an inequality of this flavor. And now this is not Hardy-Krause. This is much more down to earth. This is just the Lipschitz constant. And this is exactly this Wasserstein distance that I'll introduce in a bit. And inequality is sharp. And again, Lipschitz constants are explicit. So the question that remains, what is this W1? And the problem is to transport 2 measures. That's sort of the underlying question. If I'm given 2 measures, how do I effectively transport one to the other? And in all our cases, mu is going to be the empirical distribution of the points, and nu is always going to be the Lebesgue measure. Okay, so those are our 2 measures, and we don't try to solve optimal transport problems at great level of generality. One measure is Lebesgue, and the other is just Dirac's in the points. Oops, I just disappeared. Okay. So then the question is, if you have 2 measures, how much does it cost to transport one to the other? And instead of abstractly defining it, I'm telling you how to think about this. Think of the measures being comprised of little boxes of weight, epsilon boxes having epsilon mass. And then the cost of transporting a box that has weight epsilon for distance delta is epsilon times delta. And that's the physical cost of actually carrying a box a certain distance, right? That's the calories you expend, I guess. So what's the cheapest way to get one measure to the other measure? That's not the entire question. And that's a measure of regularity. And if it's small, then it means the points are sort of well distributed everywhere. And if it's very expensive, it means some points have to be transported a long distance, and that's a measure of irregularity. And again, I remind you, there's a nice example. If you haven't been here Wednesday, I'm not reminding you, I'm telling you there's nice examples. So suppose you have one Dirac measure in 0, which is blue, and you have two measures in A and B. So you have one measure distributed over A and B, and that has the same total mass as the blue measure. So the total mass 1, and 1 is a third. This is a third, this is 2/3, the total measure. And then transporting this big box, distance A, while you transport a third of the mass distance A, and you transport 2/3 of the mass distance B. And that's it. And again, there's an LP version of this where you punish larger distances disproportionately. So here, if you have to carry something twice as far, it's twice as expensive. And in a WP distance, that's not quite the case. So you get, the further you travel, the more punishment there is. And then there's a P through it to sort of average things out. So this would be the P version of this. And here's another example. Suppose you have 1 unit of mass centered in the middle of an interval, and you have to transport of the interval. Well, then the constant, you have little epsilon boxes, and they fill up the entire interval, and it becomes an integral. And the W1 distance is this, and the WP distance would be that. So particularly, for example, if you have n points and they're uniformly distributed in the unit interval, equispaced, then the transport cost would be roughly 1/n. And Hölder's inequality tells you the costs go up as P goes up. And for this talk, replace everything by W1 or W2. So most things will be W2, but W1 is the actual physical cost. And I think it's a very interesting notion. And maybe it's that sort of, to get an intuition, that's a nice thing to have in your mind. Okay, so the main questions I have is, if you have a nice compact manifold, and why not the sphere, right? The sphere is nice. How would you actually bound a given set from above in a way that's doable, right? I mean, there's a lot of theoretical bounds you can write down, but which ones can you actually compute, sort of, right? How would you do this? Then maybe the question sort of dearest to my heart is, on this manifold, is it possible for you to construct sequences of points that are uniformly optimal? And optimal here means have the smallest possible rate. So in contrast to sort of discrepancy problems, where it's very hard to place endpoints in a way that the discrepancy is small, here, the stationary problem is actually fairly easy. So if you want to place endpoints on a manifold to minimize this Wasserstein distance, it's not hard to see that you can do it with this cost and that that's the optimal rate. And then the question you could ask is, what's the constant in front? And I think that gets very quickly very difficult. I mean, this probably is a very, very hard problem, even in simple cases. Probably you can do it on the interval, but like the constant, here the difficulty is not in the growth, it's in the constant. And
sorry, you may have said this and I may have just missed it. That D there, that's the Hausdorff dimension of the manifold?
Yeah, and everything here is smooth and nice and not crazy. So even just the dimension, right? I mean, it's think of surfaces, so smooth, compact, nice manifolds.
Okay, thank you.
If you want to, you're hinting at Hausdorff, right? So that's sort of the more abstract version of sets, right? You could have a fractal set, and you could try to do something similar. And I haven't thought about that. It would be interesting whether this goes through. Even the stationary problem might be hard there. But so the question is, when can you do this uniformly in n? I think the interesting part is uniformly in n. So it's different because you have to keep adding points. And if you have a very nice distribution, by adding points, you might make it sort of lopsided. And sometimes you'll be able to do this and sometimes not. And I'll mention the results, but in particular, here it's an interplay of P and D. So in the one-dimensional case, there's a result of Cole-Graham that I'll mention later on as well that says you can't do this. Okay, so in the one-dimensional case, this is actually always impossible. You can't have this. In 2D, we have an example where it can be done. And then in higher dimensions, it gets sort of easier, but the question is, basically the hardest case is probably the two-dimensional case, and then the question is, what can you do? And also in the two-dimensional case, once you make P large, it might get very difficult. So I don't know. And then, so this is a leading question. How is this connected to Riese energy? So I think most people here have heard of Riese energy. It's the idea that you compute the 1 over the distance between all pairs of points and sum this up. And it turns out that is connected. So that would be Coulomb energy, a special case of Riese energy. That is connected. And finally, if there is time, and there might well not be, I'll finish with a gorgeous elementary geometric problem. So this is absolutely elementary. And I don't know how to do it. I know how to do bad versions of it. Now, this would actually have immediate implications on PDEs. So I'm not talking about PDEs here, but I'm telling you a beautiful elementary geometric problem you can explain to your grandma. And I'd love to hear any sort of input. I think it's a great problem. Okay, so what I mentioned on Wednesday already, there's this gorgeous recent bound by Peyre, which says that if I do a transport from a measure to the flat measure, that's important. It's not generally true. Then I can bound this Wasserstein-2 distance by the h-1 norm. And in particular, if I have sets of points on the torus, then this just transforms into some exponential sum estimate, right? You just plug in the definition of the Sobolev norm. And this is sort of reminiscent of Erdős-Turan or maybe Cox-Malavka, Levesque, right? Not Cox-Malavka, Levesque, Erdős-Turan, missing one, but exponential sum estimates for discrepancy. So in particular, for many sequences, this is sort of understood. So you get Wasserstein distances bounds for free. And the problem is in 2 dimensions, this is no longer, you can't write it like this. And this is the reason why Zinterhof's diaphony was never extended. But there is a trick, and I mentioned the trick on Wednesday as well, which is you can use a triangle inequality. And you just transport, you split up the problem. And first you make your measure a little bit nicer, right? Because the problem in high dimensions is Diracs are very singular. But if you replace a Dirac by a very narrow Gaussian, it's basically the same measure, right? But it's certainly very smooth. It's in all the Sobolev spaces, right? Whereas, and then you can use the Peyre estimate on estimating the bounding the cost from transporting from the nice measure to the flat measure. And we did this on the torus, and we got this sort of very nice, this is really sort of an Erdős-Turan estimate for Wasserstein distances. And it should be quite useful for a lot of sequences, but it's intimately adapted to the torus. So the question is, can you do the trick on manifolds? And the answer is yes. So if you have a compact manifold in, oops, this is wrong. God, I copied this incorrectly. This is K runs from 1 to infinity. Sorry about this. If you have a compact manifold in dimensions, no boundary, sufficiently nice, then you can always bound by sort of a similar trade-off where you pick a parameter t, and that the larger the t, the better the second term, but of course the bigger the first term. So it's a balancing between 2 factors. And here what you get is you get eigenvalues and eigenfunctions of the Laplace. So with this normalization. So the proof is the same. And what this does, it gives you a sort of a general inequality on general manifolds. But in general, you don't know what the eigenfunctions of the Laplace are, except if you're on the torus or on the sphere. So this is probably only, it's mainly useful on the torus and on the sphere, where it should be useful. And we haven't actually explored the sphere at all. So this should give you a certain, I don't know what happens when you plug this into the sphere, right? These become spherical harmonics. Should be interesting, should be an interesting tool. Okay, so to focus attention on 2 questions, given a d-dimensional manifold, when can you find a sequence such that this coffee shop problem, as I called it on Wednesday, when can you find a sequence that's uniformly balanced? At any point in time, no matter when you stop, the transport cost is optimal up to constants. When is this possible? And the interplay here is, the question is really twofold. There's a dimension d and how much you punish large transport, and those 2 will play together. And in particular, here's a I'm not writing conjecture because it's too daring, but I think the answer to this question might only depend on P and D. I think it might be quite independent of the manifold. Maybe this is wrong, but I wouldn't be shocked if it ended up being true. Maybe there's some nice universal, maybe it's even easy to prove this. You say, I don't know what the answer is, but if I can do it on one manifold, I can do it on another by sort of transplanting the points. And more or less, it's a local problem, right? But I want effective local distributions. Manifolds are locally Euclidean. So presumably, if I can do it on a unit cube in d dimensions, I can do it on any d-dimensional manifold, maybe. That would be a fun transference principle. I don't know whether this is doable. Maybe it's hard. I don't know. And a test case that I'd like to see is, you know, we have a construction on the two-dimensional torus where for p is 2, this is true. Can you make p larger? Is it still true? I don't know. We don't have the right kind of technique to answer this. Second question, can you transfer this example onto the sphere, right? That's an explicit test case. Is there such a sequence for 2 points on the sphere? I don't know. Sets, yes. Like if you know n in advance, this is very easy to do. If you want to make it a sequence, it's sort of tricky. And a second question is, you know, for sort of classical sequences that are known, what can you say about this sort of notion, right? That sort of, I'd be interested in classical sequences on the torus or classical constructions of points on the sphere. What happens, right? And some of you may have been at the Banff workshop a couple hours ago, right? And there was a nice talk about the diamond ensemble on the sphere, right? So special sets of points on the sphere that are very good. And they don't have optimal discrepancy, but one question you could ask is, you know, how far can you go up in the P? And I think by construction, they should, for example, they should be optimal in this for all P's up to infinity. So that would be interesting. Okay, so now I'll go back and I'll recall a classical combinatorial result from the 80s. That's a lot of fun. And it gives us sort of the first insight into what to hope for. So suppose you take 2 endpoints on the unit square. You take n red points and blue points, and each point is randomly picked. And then what you're going to do, we're going to match it up, right? You're going to send each red point to a blue point uniquely and each blue point to a red point. So you're going to have a bijection between these two sets. And then you want the bijection so that the sum of the distances is as small as possible. And it's sort of a classical result by now from the 80s that you can't do, and that 1 over square root n is sort of the typical transport distance that you'd expect from the scaling into dimensions. And you're going to lose a log. You're going to lose a square root of a log. It's unavoidable. And this is sort of this very beautiful result that's sort of very classical. And this is a phenomenon in 2 dimensions. So once you go to higher dimensions, this square root log disappears. And you just pay the usual neighbor scaling, which is n to the minus 1 over d. But this is, for our question, an interesting consequence, right? Because it says that if I pick random points in a unit square, then the transport cost on average is at least this. So I should have an expectation here with high likelihood, but this is constant. These quantities are fairly concentrated, so don't worry about it. If it was true that I could transport to the flat distribution with less than this, then I could solve this problem by some sort of trying. Well, okay, maybe that's not quite true. I should be more careful here. Actually, this might be wrong. Sorry about this. I'll fix the slides before I submit them. The real question is, wait, this is probably nonsense. It might be true. No, it should be true. Should be true. I'll think about it a bit more. But in any case, I think you lose a squared log even in Wasserstein 1 for the random points. And next slide, I'm safer because I'm citing someone else's results. So there's no autonomous thinking. There is a classical result from the late 60s that I don't think it's phrased like this, but later it got sort of reinterpreted like this because Wasserstein distance was only introduced in like 1970. But what they're proving is, what Dudley is proving is the following. If you have a nice compactly supported measure in 3 dimensions, then the transport cost of a random sample of points, you pick n points according to this measure, then the transport cost is optimal for random points for W1 once the dimension is 3 or higher. So once you're in 3 dimensions, if you take random points in the unit cube, the W1 transport cost is actually the optimal rate. So what you can do, presumably, well, okay, so if you pick an infinite sequence of random points, right, presumably you lose a, law of iterated logarithm kind of stuff, right? Presumably you're not always good, but it's a very good construction already. And this is what I mean by the interplay of P and D. So for W1, the problem is sort of easy in dimension 3 and higher. Or should be easy, right? I'm not giving you an explicit sequence here. I don't know how easy that is, but it should be easier, right? So if if someone puts a gun to my head and says, you have 1 week to construct a sequence that satisfies this, but you can pick the dimension as high as you want, probably it can be done. Right? If I take dimension 20, there's a lot of room to move in dimension 20. Should be fine, right? There might be ways to do it. So one question now is maybe the problem is trivial, right? Because random points already do the job, right? Maybe the question is only interesting in 2 dimensions. And that's not true. So, I mean, certainly dimension 2 is a very interesting case, but this random point asymptotic fails at some level of P. So essentially this is still true if you dial up the P up to D over 2. So again, same setup, you have a nice measure, take the measure in the unit cube, pick n random points. The case P is 1 is Dudley, and then you can dial up the P a little bit up to a certain range, and you still have it, but once P is sufficiently big, depending on the dimension, it gets harder. And random points won't do the job, but they won't be a good construction. Any question on this? Okay, so this is sort of the random points. So random points actually, so when I go back to this sort of first problem here, right? Random points actually solve this question in a certain setting. And they don't really, right? Because the fact that for every single random sample of endpoints, this is true does not mean it's true for an infinite sequence of random points, right? You need at least one more argument, and I don't know whether it's true, whether you lose a log somewhere. But morally, the problem is not insanely hard, I hope. But then as you dial up to 2, the difficulty level sort of increases in every dimension. So the larger values of P get more difficult. And P's 1 should be easy. Okay, I'm saying it is easier, it should be easy. I don't know, I don't have a good construction in 20 dimensions. We have the Kronecker construction, which works for P's 1, but it's not simple, right? It uses number theory. So now I'll go back to P's 2. P's 2 is my favorite case. L2 is the nicest, and W2 is also really nice. And I'll give you a connection between all these things and energy minimization problems that have been studied sort of independently. So I'll use the Green's function of the Laplacian. So given a manifold that's nice and has no boundary and is compact, and think of the sphere. There exists a Green's function that has this property. It solves the Poisson equation. Now, what does this mean? I don't know. Sort of tricky, right? It's roughly this, okay? So it's not true. And the Green's function does depend on the manifold that you're at, but roughly what it does is it behaves roughly like this object. Okay, so this is the asymptotic, it blows up when X and Y get close together. It blows up like this. Maybe different constant, but as asymptotic blows up like this. And then otherwise it decays when X and Y go apart. And it's always defined up to a constant, so you can force it to have mean value 0. So if you fix X and integrate over Y, you get a constant, and you just put that in the definitions, and that's good. Okay, so there's an explicit formula for this on the sphere. There's an explicit formula in the Euclidean space. There it's just this. So it's not a horrendous object. It's essentially a Riesz energy. Okay, so here's the theorem. Right? This is sort of the theorem that got me into this entire business in the first place. If you're in a 3-dimensional manifold or higher, then you can bound the Wasserstein 2 distance by 2 quantities. One is this unavoidable error, 1 over n to the 1 over d, which is also the best possible rate. And another quantity, and that's the Green function evaluated at all pairs of points, but not at the same point, right? That's undefined. That's when you divide by 0. And then you take a root of that. Okay, so there's this very nice estimate. It's just in terms of Green's functions, which you say is, maybe it's a bit abstract, but I'll make it concrete in a second. So this is the statement I just had. And again, you can think of it as an Erdős-Turan type flavor if you want, with the Green's function sort of incorporating all the exponentials. So this is actually nice because it relates to existing results. So there's an existing result which says that if you pick a manifold and you pick a Green's function, I mean, it has a Green's function, and you minimize this quantity in here, then asymptotically, the minimizing sets of points are uniformly distributed. So this is a fairly recent result. And what our result sort of says here is it quantifies this proof in a certain sense. It says, if you minimize this, then not only are you uniformly distributed, you actually have optimal Wasserstein transport rate, which does imply uniform distribution among other things, but it also quantifies the rate of uniform distribution. So Wasserstein distance going to 0 implies that the sequence is uniformly distributed. And how quickly sort of is a rate of how quickly you converge. And this also, the proof, so it doesn't follow from the inequality, but from the proof, it follows that this cannot be too small, which is, on the sphere, this is a result of Wagner from the 90s. And here's sort of a more general kind of statement for manifolds. In 2 dimensions, so this is dimensions 3 and higher. In 2 dimensions, the proof loses a square root of a log, which you just saw, right? You just saw that quantity. So in particular, it gives us a slightly different estimate for what this means for this quantity. But the question is the logarithm necessary? I don't know. It is what it is. So at this point, it's still fairly abstract, right? Because I have a Green's function, and who knows what the Green's function really is. But you can make it concrete. And on the sphere, you actually have this, there's an explicit formula, and it's complicated and has some terms and some special functions, but in practice, it tells you that this is true. On the sphere, the Green's function behaves like this. And this was good enough to get a better estimate or a more explicit estimate on the sphere. So on the sphere, again, in dimension 3 and higher, there is an estimate for the W2 transport that is the absolute necessary quantity. And then this version, this is really explicit now. There's no Green's function here. And this constant CD is chosen such that it's the limiting asymptotics for a uniform distribution. So you subtract that. You deviate how much you deviate from the optimal limiting case. And this would be the result. And
so that's the second order term, basically.
I don't know what the second order.
So you subtract the optimal value of a not necessarily discrete measures.
Right. So what happens is if the points are uniformly distributed, right? If they are perfectly uniformly distributed, then this sum by itself, without the CD and without the normalization, is going to grow like n squared because there's n squared terms. And the constant is going to be, the leading constant is going to be the average distance between 2 points. And this here, you see the average distance between 2 points, sort of. So, and then you subtract that asymptotics. So it's the leading order asymptotics in the recent energy, and you kill that off completely. Otherwise, if you don't have the constant, if this was gone, right, then this would just grow like a constant. This would be n squared. You divide by n squared, and you wouldn't get any bound at all. And here the bound you get is the deviation from the leading asymptotics. And it's actually, there's a lot of studies. So there's the group at Vanderbilt. There's a lot of active research on what the second order asymptotics of the recent energy is, right? The leading order asymptotic is always given by some rule like this. And then the second order term is sort of a bit mysterious. And here the second order term governs the transport distance. So this has a very nice application because it's known from a result of Wagner from the early 90s that this quantity scales like this. And this gives you a corollary that the minimizers of the Coulomb energy have optimal Wasserstein convergence rate. Okay, and this result of Wagner essentially is sort of the analog of the result of Wagner is this sort of statement in the general case. But on the sphere, everything's explicit. So, and there's sort of simultaneously, there was a very nice paper by Jordi Mazzo and Mas, and they sort of, it's a very, very nice paper, so I would recommend you have a look. And they really study the minimizing configuration of these energies on the sphere. And what they study is they get spherical cap estimates, but they also get, number one, it's a very good paper because it explains, the history and many other results. But it also proves a sort of an H-1 type quantity. So really a Sobolev norm of the minimizers of the Riese energy, and they get some optimal results in sort of in the relevant regime. So I think their argument would also, I think they also proved this essentially, and I think the papers came out 2 weeks apart last summer. So I think that they have also proof of this, and they prove many other very nice results. So they really trace it back to sort of results of Wolf and very classical harmonic analysis. And it's very cool that sort of these results suddenly exist, right? Because clearly you'd expect minimizers of this Riese energy. They always look so pretty. They should have a very small spherical cap discrepancy. So I recommend this paper. Okay. So now I'll go back to the coffee shop problem, and I mentioned this on Wednesday. The problem is again, it's the same. Okay, I had the problem enough times, right? So I'll just state it now explicitly. How do you build a sequence on the unit square such that you have sort of optimal rate of growth, or how do you do it in general? And in one dimension, you can't do it. And in two dimension, you can, but the two-dimensional construction is hard, and how do you actually do it on a manifold? Right, so that's sort of the general question, right? So we have, so Lewis Brown and we have this result in 2 dimensions and higher that gives you an explicit construction on the torus. And it really uses the torus, and it really uses number theory, and it's a very torus type argument. And now if it's a general manifold, is this still true? I think it is. I think you can still solve the coffee shop problem. But how do you do it? And we don't know, but we can do it in 3 dimensions and higher. So again, so sphere is maybe a good test case, and the 2-dimensional sphere is probably the hardest case. So to summarize sort of this notion I had all the time, 1 dimension you can't do, 2 dimension you can probably do it. 3 dimensions probably not that hard, but I don't know what that means. Right? I think in 8, I don't know. I think 2 dimension, I think if you understand 2D, you can do all higher dimensions fairly quickly. That would be maybe one clarification. And usually things get harder in higher dimensions. I think here it gets easier. Okay, so it turns out we can solve it on a manifold. And we can solve it in all dimensions 3 and higher with this estimate. So it turns out there's a very simple trick sort of, which is a greedy procedure, which says, how does this quantity change when you go from n to n plus 1? Well, you have your original double sum, and then you have, okay, I lost a factor 2 here. You have 2 times the interactions of all the existing points with the new point. That's algebra. And now it turns out the Green's function has mean value 0. So if I integrate over what this point could be, it's on average 0. So since it's 0 on average, I can always pick the next point in such a way that this quantity goes down. I can make it negative. Maybe not very negative, but it's less than 0. So what you can do is, there's a sort of a greedy sequence, which is given any set that you have on a manifold. You look at what this object is, and you find a point xn plus 1 that makes this as small as possible. And since the mean value is 0, there's a choice where it's not growing. There's a choice where the sum doesn't go up. So the sum doesn't go up, but you keep dividing by larger and larger numbers, and this also decays. And in principle, this tells you that if you sort of just greedily pick this minimum of these energies, you're going to get an optimal coffee shop location solution on any manifold. Now, it's not explicit, the construction. How do you do this, right? But it is really interesting. So I claim that this is actually an amazing sequence, and I apologize for people who've been at the Banff meeting. I'm going to repeat 2 slides, but this is a really, so, you have this sort of abstract stuff happening here, right? And what's G, you don't know. If you make it concrete, it gets really, really interesting. So let's make it concrete. let's go to one dimension. And Louis actually talked about this at the webinar a couple of weeks ago, but it's so fun that, one can talk about, I can talk about this for hours. So suppose we're in a unit interval. Okay, so torus, endpoints identified. The Green's function of the Laplacian is actually explicit. And it's nice, and it's a polynomial. Okay, so it's just given by this. So what you can do is you can fix this function, and you can just write down, this is what it looks like. This is what the Green function of a Laplacian looks like when you place a point in 0.2. And it's scaled to have mean value 0. That's where this constant looks suspicious, right? It comes from the fact that it's mean value 0. And it's also, for people who are interested in this, it's also the polynomial in the definition of Zinterhoff's diaphony. It is the second Bernoulli polynomial. And it's also the result of a Fourier series. So this is a very interesting function. So what you can do is you can do exactly what I said. You have a set of endpoints, and then you can sort of assess the notion of energy, which would be how much your sum grows when you add the point x. That's what it is. So given my 5 points here, 1, 2, 3, 4, 5, this gives me a cost function which tells me if I take this point here, this is how much double Green sum, this abstract quantity, how much it goes up or down, and it goes down. So what we can do is we can say, okay, you know what, let's find the minimum of this function. Because the minimum of this function, it's less than 0, because the mean value is 0. The minimal value means the sum's not going to go up a lot. So you're at the point where the energy is minimal. Okay, so now we have sort of a fun rule. We have a set of endpoints, and then we just construct this energy function, which is easy. It's piecewise polynomial, right? This is a piecewise polynomial function, piecewise quadratic polynomial. In each segment here, it's actually some sort of a parabola that goes upwards. That's all it is. You pick the next point as the one that minimizes this quantity. And when you do this, on the unit interval, you seem to get a low discrepancy sequences independently of what the initial set was. And the discrepancy is as good as van der Koopman. Down to constants. Louis actually did some nice experiment where he plotted this, and he said, okay, here's the van der Koopman discrepancy, and here's the discrepancy of this sequence that you get from starting from 2 random points. And after like 100 terms, they sort of, they circle around each other. Sometimes van der Koopman is a little bit better. Sometimes this is a little bit better. It sort of goes around. So it's a very interesting sequence. And we know relatively little. What we do know is you don't have to take this function f, this polynomial. In fact, you can take pretty much anything as long as the Fourier coefficients are positive and are not too small. So for this special polynomial, the Fourier coefficients decay like 1 over k squared. If you take anything where the Fourier coefficients decay at most at this rate, when they decay at this rate or slower, numerically, the sequence is always amazing. So for pretty much any f that is positive definite, meaning positive Fourier coefficients that don't decay, that aren't close to 0 all the time, the sequence seems to be amazing and as good as van der Koopman, quite independent of the function. And Florian Pausinger has a great result, says that for very general f that are symmetric and convex, that's all you need. You actually already have a bound, which is surely not optimal, but it's great because it's so generally applicable. And then we have some Wasserstein bounds. So this is the one you've seen. And I have some recent result on what happens when you take a fraction Laplacian, because then there's some amazing stuff that happens. There's some miracle. Okay. And the fun thing about this proof is that I don't know how to do it for any other function f. This is the only function f for which my trick works. And what's special about it is its Fourier series expansion is very nice. It's 1 over k. It's particularly special. There's some closed form algebra magic. So sometimes it's a very bad proof because it doesn't generalize at all. Okay, so this is all sort of stuff that came out of out of this sort of simple argument that we do know how to get optimal transports. We know how to solve the coffee shop problem for piece 2 in dimensions 3 and higher on any manifold. Now, what about piece 3? What about piece 4? We don't know. What about 2 dimensions, right? What about the 2-dimensional estimate? Well, the same argument applies, but you inherit the squared log factor. So we can solve the coffee shop problem for piece 2 on any 2-dimensional manifold up to a square root of a log. And it's not clear whether that's necessary. Okay, so there's a lot of, Luis and I have a paper in the Journal of Complexity on this, where we try to sort of really explain the problem, and we give a lot of background. There's a lot of pictures. And I think our confusion is visible on every page. We just don't know why this thing is so good. And it must be good for an interesting reason. And this, yeah, you can have a look at this, right? But it's not, this does not explain why this does not explain any of the other things. It's not the right answer. And yeah, as I said, you have a logarithmic loss in 2D with this construction. So whether you can do this generally, in the general manifold, or maybe even larger values of P, we don't know. Okay, so this question is wide open. Can you do this on a sphere, 2-sphere? And in particular, there's a construction that Luis and I have on the torus, which is very nice, badly approximable vectors. Is that maybe true for larger values of P than 2? It works for 2 because of all these Fourier estimates, harmonic analysis, gorgeous. The moment it's 2.1, the sequence is still very good. Maybe it can do 2.1. We don't know. Completely open. And there are several constructions on the sphere. Maybe some of them have this property. Maybe none of them have this property. I don't know. Might be a hard problem. Okay, so this discrepancy. So what we have is we do have on the sphere, right? We always have this Kantorowicz-Rubinstein duality, the Cox-Malawka inequality for Wasserstein. So in particular, we also have W1 is less than W2. So we can bound this from above by W2, and then we can use all our estimates, in particular use this on the sphere. And on the sphere, this becomes explicit because we know the eigenfunctions on the sphere. So does this lead to any new type of integration bounds? I mean, you can sort of see that it does, right? Because you plug this in and it sort of works. But what does this actually mean on the sphere? If you plug in harmonic polynomials, is this a known quantity? Is this, you can also write in terms of the Green's function on the sphere, right? But is this a new estimate? I don't know. What is it? So I like it. I like the thought of this. I've never worked on the sphere really, so I'm not too sure what this means. But there are interesting things on the sphere. So for example, as a result of Grabner, which is really cool, and I'm not defining all these quantities, but he's producing a bound on the spherical cap discrepancy that has an Erdős-Turan type flavor, and the exponentials are replaced by spherical harmonics. So this is all somehow related, right? Probably you can bound Wasserstein distance in terms of spherical discrepancy, right? Because if every cap has the right number of things roughly, you don't have to transport too far. And it's all aligned, right? Because we also have this Wasserstein transport bound for general manifolds. So somehow this should all be sort of related. And I just don't know. Okay, so I think I have maybe 10 minutes. Yeah. So if there's too many Green's functions and too many manifolds and too many things happening, I'll tell you about a very, very simple problem at the end. Gorgeous, geometric, and absolutely down to earth. So the question is so I proved the following. So I found this result by coincidence, okay? I'm completely honest about this. I ran into this by mistake. I would have never thought of this. It dropped out of, you do one of the proofs and then you see what happens if I compare this and this, and suddenly I had this inequality. And I'm like, ooh, what is this? So this is a coincidence discovery, but it's really cool. So suppose you have a function on the standard torus, or periodic if you want, and it has mean value 0. Then there's the positive part and there's the negative part, right? There's an f plus and there's an f minus. And the positive part is equally big as the negative part because the mean value is 0. And now one question you can ask is, how much does it cost to transport the positive part to the negative part? Right? There's a red measure and there's a blue measure. And somehow, so you can transport one to the other. And I can just use standard W1 transport distance. I can say, how big is this? And I realized, I didn't realize that I found by mistake that there is such a bound, right? And here's the following: if there are very few roots, right? If there are very few roots, then there's a big chunk of positive, and there's a big chunk of negative, and there's another big chunk of positive, and you have to transport a long distance. And if there are many roots, then there's a positive part right next to a negative part, and then the transport might be cheap. But the idea is there should be an uncertainty principle, and there is. And this is sort of the bound that came out. I don't know whether these LP spaces are optimal, but you can look at a simple example. The example is sine nx. And you see that the transport constant is roughly 1 over n, right? Because each positive bump has a negative bump that's exactly itself mirrored. That's distance 1 over n. So I can just transport each hill to the adjacent valley. And that gives me a W1 distance of n to the minus 1. And it also has n roots. So these two quantities sort of cancel out, and this is constant 1, right? I mean, this doesn't change for different values of n. So this inequality is sort of nice. And my question is, maybe, what happens if you put a p here? Maybe if you put a p here, these p's change, maybe these LP spaces change, I don't know. And I really like the question, because how many elementary inequalities for functions on the real line do you know? Like, I mean, I thought I knew all the inequalities for functions of one variable, right? You can only go up or down. But this is a new one, right? So what if you put a p distance here? Maybe you can sort of improve this a little. I don't know. I don't really know what the extremal cases are. Can you put an L5 here? Probably not, but maybe. And what happens in higher dimensions? And this is actually, I call this a Wasserstein uncertainty principle, because this is an old slide which has gotten very political. But it is the following, right? I mean, if you have few post offices, so think of your function f as, are you inside a post office or not? And you're positive if you're in a post office, and it's negative if you're not. Then the zero set is just sort of the walls of the post office, which counts how many post offices there are. And this is the typical traveling distance to a post office. So this actually has some nice geometric interpretation. And so here's a picture, right? So suppose you have the red measure, looks like this, and you have the blue measure. So red measure means the function is positive, blue measure means the function is negative. And if it looks like this, then you sort of have to have these black zero sets. So the statement should be the following: if I can transport the positive part of a function to a negative part of a function relatively quickly, then there has to be a large zero set. And the zero set in general is d minus 1 dimensional. And that's sort of the statement. And it turns out I have a proof in 2 dimensions. So if you have a function on a unit square, and you look at this uncertainty quantity, right? That the cost of transport from the positive part to the negative part, sorry, mean value 0, with mean value 0. With mean value 0. So if you transport the positive part to the negative part, if this is very, very small, then the length of the zero set, this is the Hausdorff measure, the one-dimensional Hausdorff measure, the length of the zero set has to be very large. And conversely, if this is very, very large, then this can be small. Think of alternating plus and minus very frequently. So this, I think, is an absolutely fantastic inequality. I'm skipping this. So in general dimensions, we don't have this. So if the dimension is 3 or higher, we have that there is such a statement, but the exponent here is 4 minus 1 over d. This was then recently improved to 2 minus 1 over d. And both the 2 of us and the 3 of them think that the right constant should be 1. So there should be sort of a general inequality like this, and it is proven for 1 and 2 dimensions. It's open in 3. We don't know whether it's true or not. But this is a Wasserstein uncertainty principle, and it would have immediate implications for the zero set of Laplacian eigenfunctions. So that actually, you can, if you prove an improvement on this, you can write a PE paper. I'll write you the introduction myself, and you can you've proven it, okay? That this is the bottleneck of PDs right now. We need to have this estimate in dimension 3 and higher, otherwise we're stuck on what Laplacian eigenfunctions are doing. Okay, so this, I'm skipping this proof as well. It's not that important. What's important about it is it's easy. This is not a very tricky proof. We use the isoperimetric inequality at some point. It's not hard. And with this, I conclude, and thank you very much for having such a fun seminar.
All right, thank you very much for this very nice talk. So please, people, applaud or just push the applause button. All right, as usual, are there any questions? Okay, perhaps people will need to think about it. So perhaps let me remark something. If you're interested in the green functions or more concrete green functions, there's actually a paper by me and Carlos Bertrand where we have calculated the green function for SO3. And we also have bounds for the green energy. And I believe as soon as you know something about the eigenfunctions after Laplacian, you can just recycle the proof and obtain at least lower bounds for the green energy.
Oh, that is fantastic.
Yeah, it's due to LKIS. So this was really nice and very helpful. So anyways, for SO3, which is a three-dimensional manifold, we obtain essentially that the green function can be bound is of the order n to the 4/3. So you just really obtain essentially one in your case 1 over n to the 1/3 power. So yeah.
Wow.
Oh, and related to this problem, I believe that there's a prize that Demir is offering for, what is it? Anyone that can, what was it? Give explicit eigenvalues for.
Yes. So the whole point is we have an explicit construction for the green functions, right? But I need the eigenfunctions in order to write it down. And the eigenfunctions for these rotations group are very special functions from physics, but we have not been able to find those for SO4 or SON. So I had this open problem, find these eigenfunctions or these actually irreducible representations for SON. And if you can do this, you'll get either 50 euros or 80 kilograms of onions as a prize. And still open actually. So if you find this, you can claim the prize.
So
now, yes, please.
So I do have a question. So Green's functions are not something that I'm that familiar with. Like I've come across them. I've heard talks where they've been involved. And right, you were able to explicitly give one for what it was on the interval. I mean, on general, is that something are Green's functions something that generally can be explicitly written on manifolds, or have some form that like is close enough to being explicit that makes them very useful?
Maybe Damir has better answer than I do. I think you roughly know what it does, but once you care about what its value actually is, it starts getting tricky.
I mean, you can actually write down a power series as soon as you know the eigenfunctions of the Laplacian, right?
Yeah, but you never know, right? I mean, okay, once you know the eigenfunctions of the Laplacians, there's a formula which is very simple.
Yes. And just write phi jx times phi jy divided by the eigenvalue, lambda j, and you sum this up, and it's the green function. And now just calculate and try to find something simple out of it, which is, of course, not that easy.
So the formula you have on every manifold, once you have a nice manifold, a nice eigenfunction, sometimes this infinite sum simplifies to an explicit closed form expression. That's what happens on a torus and on a sphere. General manifolds, it doesn't. But you also know, you know what the Green's function like roughly does, right? It blows up at a certain rate 1 over d minus 2 on nice enough manifolds, and you have sort of a gut feeling what it does, but I think not enough to really work with. If you need the closed form, there's very little you can do, I think. Although apparently SO3, you can suddenly, it's become available, which is cool.
Yeah. Lucky coincidence, I guess. Let's see how things work out. Okay, any more remarks or questions?
Yes, I also have a question. So, hi. So you mentioned a result on a compact manifold. You can bound the W2 Weierstrass distance by something like the infimum of t plus some
Yes.
exponential function. So I'm thinking for like a nice manifold, say a compact manifold with a positive, with Ricci curvature bounded from below, this W2 distance can be bounded by Fisher information divided by the Ricci curvature. I mean the lower bound of the Ricci curvature. Yes, this result.
I would believe this.
Yes, my question is, can we compare, maybe this is too, this is a dumb question. So for the right-hand side, I mean the left-hand side, not on sphere, but on like arbitrary compact manifold with Ricci curvature bounded from below by a positive constant. This left-hand side can be bounded by Fisher information divided by Ricci curvature. I think this is a result by Villani. So can we compare this Fisher information thing and your estimate, or are they relevant?
Okay, the short answer is I don't know.
Mm-hmm.
The irrelevant answer is thank you for proving my point that this is connected to many interesting things. That's the relevant answer. And the other answer would be, I don't know whether people, so for Fisher information, right, that's interesting. I don't know whether people considered sort of this for point sets? Have they used it as a measure of regularity? Maybe not.
No, that's why I feel like this is interesting, because this is a new bound for the W2 distance.
Right. So does Fisher need both distributions to be continuous? The density needs to be.
Yes, it has to be a nice distribution.
Okay. Right. So, but then what you can do is you can take for a given point, you can sort of do something very similar where you replace the points by very narrow Gaussians. Mm-hmm. And then you use the Fisher distance for the Gaussians. Mm-hmm. And then maybe you pay a price of some sort, you punish how far out you can be, and that gives you a notion of discrepancy, and maybe it has this kind of Erdős-Turan expansion via an argument like this. That I don't know.
Okay.
It's very interesting.
Yep. Thank you.
Okay, are there any more questions? Okay, let's perhaps have a last remark for me. So, Stefan, you mentioned perhaps there is a sort of an estimate of the discrepancy by the Wasserstein metric, right?
Maybe the other direction, this one?
Yeah, I guess so. So I'm trying to copy and paste a link to a paper where actually there are some relations between different measures, and there is also among them the discrepancy in the Wasserstein metric by Alison Gibbs and Francis Su on choosing and bounding probability metrics. But for some reason, I cannot copy it. Let me just. Okay. Yeah, no idea why. Okay, sorry, just doesn't work. Okay, I'll send you an email. Might be interesting for you, I guess.
Yes.
Okay, any more questions or remarks? Okay, let's perhaps stop the recording and see if things happen afterwards.